Welcome. In this session, I will discuss the properties of limits and calculating some simple limits by using this. Previously, we discussed finding limits by using values, tables of values, or graphs. These are limited, these are restricted in the sense that they allow only certain amount of precision. They're also subject to certain uncertainty because we don't know what happens as we zoom in. You might find something new happening. The properties of limits allow us to calculate certain limits more systematically and with greater certainty. There are three sets of properties of limits that we will use. First is a general thing that applies to combinations of functions. This basically says that limits distribute over arithmetical operations that are defined. To be precise, since addition, subtraction, multiplication are always defined, limits distribute over them. So to be specific, for example, if I have two functions f and g, and as x approaches a, f approaches L, and g approaches m, then f plus g approaches L plus m. F minus g approaches L minus m, and f times g approaches L times m. With division or fractions, we need to be sure the denominator is not 0. So if f approaches L, g approaches m, and m is not 0, then f over g approaches L over m. With exponents, we have to be more careful. Nth roots are always defined if n is an odd number, so that's fine. Exponents, even if the exponent is irrational, are defined if the base is positive. So if L is positive and f approaches L, then f power g approaches L power m if m is the limit of g. The one problem is even order roots where the limit is 0. The trouble is that if I know the limit of f is 0, I still may not know if f is positive or negative. So for example, I cannot tell if the square root of f of x is defined. If I know in addition that f is always non-negative, then I know the square root is defined, and then we can say that the limit of the square root is 0. So we need to be careful with this particular combination. But otherwise, limits work the way we expect with respect to arithmetical operations. The second set of input is limits of specific functions. Limit of constants and limit of the function x are the values. This is kind of obvious. If I have a constant function, it never changes, which means that the value of the constant function is the constant no matter what x is. So as x gets close to a, the function's value is as close to the constant as you can get. And the limit of the identity function, limit of x as x approaches a is a. If x is getting closer and closer to a, then the function x is getting closer and closer to a. It turns out these rules also apply, this property also applies to exponentials and logarithms. The third property is the important one. This is what distinguishes limits from value. If two functions are equal, at least when x is close to a, except possibly at a itself, then either both don't have a limit or both have a limit and the limits are equal. So in other words, limit depends only on the value of the function near the number a, but not at a itself. We'll see the significance of this when we calculate limits next. So let's see how these things work in practice. First, we'll look at the limit of a polynomial. The limit of x squared minus 2x plus 3 as x approaches 1. First of all, because limits distribute over addition and subtraction, we can find limits term by term. So the limit we are trying to calculate is the limit of x squared minus the limit of 2x plus the limit of 3. Now 3 is a constant, so the limit is that constant 3. X squared is x times x, which means I can find the limit factor by factor. So the limit of x squared is the limit of x times the limit of x. And same way, limit of 2x is the limit of 2 times the limit of x, and limit of 3 is the constant 3. Now I have limit of a constant or limit of a limit of x in each of these, and we know the limit of x is whatever x is approaching. So the first term would be just 1 times 1. Limit as x approaches 1 of the constant 2 is just 2. So the second term is 2 times x. And then I have plus 3. So let's just take a moment, look at this. If I have a polynomial, this is always going to work, which means that for any polynomial, limit equals the value. Of course, we started the whole discussion by looking at functions which are not defined. So the very first example we did, if you recall, so we were trying to find the limit of this quantity, 16t squared minus 64. As t approaches 2, we looked at the values and found the limit. Now let's do the same thing, but now using the rules for calculating limits. The point is that 16t squared minus 64 over the quantity t minus 2 can be simplified algebraically. We can factor the numerator. First factor out the 16. So the numerator is 16 times the quantity t squared minus 4, which factors as t plus 2 times t minus 2. So we can reduce the fraction by cancelling the t minus 2, and I have 16 times the quantity t plus 2. But there is a small issue when we think of this as functions, which is that when t is equal to 2, this fraction is not defined, but the polynomial is. So as functions, what this really says is that if t is not equal to 2, these two functions are equal. And if you recall, the second property from the previous slide says that if two functions are equal, except at a certain number, then they must have the same limit at that number. So the limit of 16t squared minus 64 over the quantity t minus 2 is same as the limit of 16 times the quantity t plus 2. But now this is a polynomial, so we can argue like in the previous example. First, distribute the limit over the multiplication. So I get limit of 16 as t approaches 2 times the limit of t plus 2 as t approaches 2. 16 is a constant, so the limit is 16, and then I can distribute the limit over the sum in the second factor. Limit of t as t approaches 2 is 2. The limit of 2 is, since 2 is a constant, just 2, so I get 16 times 2 plus 2. And that's 64, which is what we got before. So this is basically an illustration of how we can apply the limit rule step by step, and we'll continue the discussion next time. Goodbye for now.